So we can use the derivative of a function to determine where the maximum, the maxima, or the minima are. So if you just look at this graph, then obviously this point over here is a maximum, the top of the hill, and then this point over here is a minimum. So let's look at what the derivative does at these points. So remember, of course the derivative is the slope of the tangent line. So at these maximum and minimum points, the tangent line is horizontal. So that means that at these points, the derivative is equal to 0. And so let's look at the maximum. So before this maximum point, the derivative is positive because it's climbing, the graph is kind of climbing up. So the slope of these tangent lines is positive before the minimum, the maximum point. And then at the maximum, it's equal to 0. And then afterwards, the graph starts going down. So the derivative switches to negative. And then at the minimum point, before the graph is decreasing, so the derivative is negative, and then after the point, the derivative goes back to positive. So the derivative switches signs, after these maximum and minimum points, and that's a key feature. So notice how we say this is a maximum, but the graph, as you can see, it goes on to infinity. So obviously this is not the highest point in the entire function. So we call these kinds of maximum and minimum, we call them relative maxima or minima. So these relative maximums are only the max value in some area around them. They're like the max or the min in the local neighborhood, but they don't have to be necessarily the max or min value for the entire function. So if we want to see the true maximum or minimum on some closed value, then we call that an absolute maximum. So when we have a closed interval, then the absolute maximum or absolute minimum is the actual highest and lowest value inside that interval, including the endpoints, of course, because it's a closed interval. So finding an absolute maxima or minima is a little different than finding a relative maximum or minimum. So if you just want to find a relative maximum, then you have to look at where the derivative is equal to 0 and where the derivative changes sign. But if you want an absolute maximum, you have to look at all of those points as well as the endpoints of the interval, because the absolute max or min could occur at the endpoint where the derivative is not necessarily 0. So finding absolute maximums, you have to check these points where the derivative is 0 as well as the endpoints and see which one is higher or which one is lower depending on what you're looking for. And you also have to be careful because the relative max or min can sometimes occur when the derivative is undefined instead of equal to 0. So for example, this function here, this point is clearly a relative minimum, but the derivative does not exist here because it's a sharp point. So you just have to watch out for things like this. So we've already established these facts, but we're just going to go over them again. So a function has a relative maximum at some y value if for all values of x around this point, then this maximum is higher than any other y value. So basically it's a relative maximum if you can find some neighborhood that it's the highest point in. It doesn't have to be a really big neighborhood, it just has to be some interval. And then a relative minimum, you have to be able to find some interval or neighborhood where that point is the lowest point out of all the y values. And so when the graph is going up or when it's going down, the formal term for that is increasing or decreasing. So a function is increasing when the derivative is positive, and because the tangent lines are pointing up, and decreasing if the derivative is negative. So if a function has a relative maximum or minimum at some point, and if the derivative exists, and remember that sometimes the minimum occurs when the derivative is undefined, but if the derivative exists, then the derivative must be equal to 0. And also, the derivative must change signs around this point. If it changes from positive to negative, it's a maximum. And if it changes from minimum to negative to positive, then it's a minimum. So, as an example, let's find the relative maximum and minimum for this function here. So the first thing you want to do is find the derivative and then set that equal to 0. Because remember, all the relative maximums or minimums will occur when the derivative is equal to 0 or when it's undefined. So it looks like we can't get an undefined value for the derivative here, so they must occur where it's equal to 0. So we see that the derivative is 0 at these points, -4 and 3. So these are the possible x values that a max or min could occur at. And by the way, you'll also hear these points, the x values where the derivative is 0 or undefined. They're sometimes called critical points. So we want to test these critical points to see if they are actually a relative max or min. Remember, one other condition is that the derivative has to change sign around these points, or else we don't have a relative max or min. For example, this function here, you can see that the derivative starts at positive, it's going up, and then it goes flat, so the derivative there is 0. But after that, it starts going up again, so the derivative is positive, 0, and then positive again. So we don't have a maximum or minimum here, because the derivative does not change sign. So let's test these points. So one way to do this is to make a number line with these critical points on it, and then test the value of the derivative around these points. So now we pick one value in each interval. So here we can choose 0. So plug 0 into the derivative and you get a negative number. So this interval is negative for the first derivative. And then we plug in a random value here, say -5, we get back a positive value. And here we'd say we can plug in 4 and we get back a positive value again. So we can see that at each of these points, the derivative switches values. At -4, it switches from positive to negative, which means -4 is a maximum. And at 3, it switches from negative to positive, which means it's a minimum. So we found 2 points, one relative max, one relative min of this function. And there's another test we can do once we have those critical points to see whether it's a max or min, instead of making this number line. And that way is to look at the second derivative of the function. So remember that the second derivative is the rate of change of the first derivative. So we can think of it as the rate of change of the slope of the tangent lines to the graph. So let's say you find a critical point, and then the second derivative at that point is negative. Well, that means the rate of change of the first derivative is negative. So the slope of the tangent lines are decreasing. So that means it must be a relative maximum. Because if you think about a maximum, on a hill, then to the left of it, the derivative starts at positive, and it gets less positive, and then at the maximum it's 0, and then it goes to negative. So the derivative is decreasing on that interval, so the second derivative must be negative. If the second derivative is positive, that means it must be a relative minimum, because the slope of the tangent lines are going from negative to 0 to positive, so they're increasing. So let's look at another example of finding the relative maximum and minimum. So let's say we want to test these points in the previous example using the second derivative test instead of the number line test. So the second derivative of this function is going to be 12x plus 6. So all we have to do is plug in negative 4 and 3 into the second derivative. So at negative 4, the second derivative is negative, which means it's a maximum. And at 3, it's positive, which means it's a minimum. So another thing we're going to look at is another meaning of the second derivative. So the second derivative can also be used to determine something called the concavity of the graph. And the concavity is basically which direction is the graph is curving in. So this section is called concave up because it's kind of facing upwards, and this section here is called concave down. Another way to look at it is when the graph is concave upward, all the tangent lines to the graph are going to be below the curve. And in the concave down interval, all the tangent lines are above the curve. So again, we can determine the concavity through the second derivative. If the second derivative is positive, then it's concave up, because here the slopes of the tangent lines are increasing. You can see here the negative, they're getting less negative, they go to 0, and then they get more and more positive. When the second derivative is negative, then the graph is concave downward. And then we also have these points where it switches from concave up to concave down, or vice versa. And these are called inflection points. Here the second derivative is equal to 0, and the second derivative also switches signs around these points.